So the objective of this afternoon's session is to give you a simple introduction to MPI, and then the lab session later will try to encourage you to try out some of these commands. Saurav was going to try out some of the commands in an instruction sheet. He's at the computer center, I think. Let me give you a preview of what he might be trying. So, where is it? Yeah. So again, I'm keeping all this material in that on that location. So today's material will be found in session slides, and then this is like session 10 and 11 that we are doing. So I have created session 10, 11 MPI code and slides, and also session 10, 11 practicals. That's what I have created. Let us take a look at session 10, 11 practicals. The practicals will be partly started today, and it will continue on to tomorrow. MPI programming is the goal. We will use a tool called ISP to learn MPI better and also to find bugs in MPI programs. So that's what ISP helps with. I should tell you right off the bat that most people write MPI programs with the intent of gluing together computations that happen on a distributed system. And well-written MPI codes use only simple, safe constructs of MPI, such as MPI send receive, MPI barriers, or even MPI collectives as they are called. A barrier is one of the collectives: reduce, scatter, gather. It's a very well thought out library when you use MPI at that level, and things largely work okay. But the complexity of each of these commands is pretty high, so we'll have to slowly understand each command, go through several examples. But if you start using several point-to-point commands and some of their special variants, MPI codes can be made to work and can be understood. But very soon we'll get into a territory where even the experts that I talked to when we were doing research in this area did not understand the outcome of a 10-line MPI program. You ask them, give them a 10-line MPI program, and ask them to predict its behavior, all possible behaviors. It's not possible for them. And then we told there are certain hidden facts about this MPI program, such as if you increase the amount of buffering that's available for certain sends, deadlocks can increase. They didn't believe that, so we had to actually show it. So it is kind of a very complex API when you look at it at that level. So we had to take our choice. Do we want to just use a small set of MPI primitives and use those well understood simple primitives and use it for large applications? That's possible. But often you will find yourselves going into these esoteric areas of MPI where you will be using point-to-point operations and special features of them, where if you are not sure of all their outcomes, testing will not find the bugs. That's the other thing. If you can run it 1,000 times, 1,000,000 times, it won't find the bugs. So there are certain accelerated bug finding techniques that you might want to use just to gain some understanding of what more can be revealed. So if you have a machine that can be scheduled in a certain way, like you march one process at a certain speed, then stop that process, march another process at a certain speed, stop that, march another process at a certain speed, then come back to this and march. So if you gently control the rate of execution, then you can hit those bugs. But those are extremely rare. It will never happen in field. So there are, I'm just telling you a general layout of how MPI is learned and used. The other thing is that MPI has been around as a standard for such a long time, and its adoption is a success story of the highest proportion. So it is going to never go away from HPC. In fact, MPI is getting more and more complex and rich. There is MPI 4 with even variations of this so-called collective commands, such as split collectives. You start a collective operation and finish it later. So MPI has a long life ahead of it. So it's good to learn it and use it. I am a user of MPI at the level of software engineering issues of MPI. Many people use MPI to create parallel patterns. Many people don't even write MPI code, they'll prefer to generate MPI code. Some of the experts I talk to never write MPI code, or even for that matter OpenMP code. They write code in a special dialect of Python, SymPy, symbolic Python. Then they know how to calculate those symbolic Pythons codes which are very close to the mathematics they want to model, and they have code generators at the back that spit out MPI code. In a framework called UINTA that I'll briefly talk about on Friday and Saturday, the user specifies a task graph. So remember this graph I drew for fork join computations when I talked about work and span. Okay, so dependency graph. So computation A has to happen, then B and C are enabled to go concurrently. B and C have to finish before D happens. Once you have a task graph and each node of the graph is a certain computation in this case a combustion calculation, the task graph compiler comes in and compiles MPI code and then even arranges for data movement. So that is a good use of MPI as a low level assembly code, because once you debug that code generator, you are in a safe land. But at some point we'll have to face the real complexity. So I'll show you this ISP tool. Hopefully that will help you learn it. ISP is one of our group's tools that we created around 2006, and it was created by some very good PhD students and some even undergraduates, and the code has been shown around a lot. We don't even use it now, it's lying around, but recently I started using it again thanks to these tutorials, and when I booted it up and try to install it, it relatively installs fine, no problem. The code is well written. Okay, so install ISP and check that it is working, which is what we will do today. ISP is only an assist to understand MPI. Real MPI users don't use ISP. They use MPI CC and MPI run as the commands. MPI CC as opposed to CC, and MPI run as opposed to MPI running the MPI. Here we have two commands called ISP CC and ISP. The names are slightly confusing. And ISP UI helps you visualize the execution. Okay, so we'll give you these instructions today. So if all these steps work, then you are ready to try out ISP. So that's what we'll be making sure when you go to the lab. Then the second part of this write-up, I thought I'll take a mini survey as to how we are doing and how we can intervene and help, plus some fun quizzes in the middle. Austin Cherian introduced the acronym ILP. Then I was chuckling because I already mentioned EPI and IPS. So now you have three words you can use against your friends and surprise them. Okay, they may not know it. And if you know other words that you want to contribute to this list and cause a net headache increase, that'll be fun. Okay, so let us keep collecting these fun acronyms that are used in HPC and computing. That's one thing. Did you make progress or finish session 2 practical? Some of you were doing that yesterday. So this will be printed out and given to you by Jairaj, and you can answer these when you get it. Did you make progress on session 6 practicals? If not, no problem. We'll allow you more time later. 7 practicals OpenMP. These are the things that we are hoping to do. Do you wish to review any of these topics or have more lab time? Just to know. This is a fun thing that Austin Cherian threw up on this slide, so I said fine. So I didn't talk about loop dependencies that much, but since this came about in his vectorization, you can start thinking about, is this a parallel loop? This is one of the things that we kept talking about. We didn't really discuss it mathematically accurate or anything. Can it be run in reverse? Does it matter which order in which you go through that index space? The answer is obviously clear, that every I lane is mindful of its own work. The I+1 doesn't interfere, so it can be done. Did you observe speed up as you increase the number of threads or in any example? Clearly, you should not go back without having studied some scaling. So try to get those happen for some OpenMP or some MPI examples before you go. Ideally, OpenMP will be easier. MPI, we don't know how we are going to run on a large machine and all that. Then here are the things that we are going to study as far as MPI goes. I will be showing these examples. These are 7-8 line pieces of code where some of them will deadlock, some of them will match and run okay. You should be able to reproduce that in the lab. I will show an iprobe command that you can try out in the lab. We'll try a very simple numerical integration program, which again is a very simple textbook example. It might give you some opportunity to study strong and weak scaling, which is a concept we studied last time, which is strong scaling means keep the problem size fixed, just keep increasing the number of processes in this case. Do you see any speed difference? These may be too small an example that you don't see speed increases, but maybe we can add some dead weight to the code, like a big busy loop in the middle, so as if it is computing something. We can do three variants of Pi, Pi with MPI, Pi with MPI plus OpenMP. These are extremely short, but it's good to see MPI plus OpenMP getting used in one page of code. Then there are four variations of a matrix multiply. Hopefully I will be able to go through that. Again, it shows you different things you can do. Then there is an odd even sort. Maybe I'll discuss that only tomorrow. It has nice visualization. So that's the lab material that is lying ahead. So let us look at the slides now. Yeah, so an overview of MPI. So this is such an old slide. I had given a tutorial in 2009, and I looked at some of my old slides and said some of them still make sense. The diagrams have changed, the machines have changed, but some of the ideas still are okay. I won't have too many slides anyway. So the largest machine then was one of these IBM machines, and Roadrunner was there. But the choice is a choice for large-scale parallel computing. So I even said continued and foreseen ubiquity of MPI. Well, that is true even 9 years later. Runs everywhere, especially on expensive state-of-the-art supercomputers. Very mature codes exist in MPI. Nobody can re-implement it easily, hence it will live on. Performs critical simulations in science and engineering. And our contribution, ISP, was pitched in that workshop as a way to dynamically analyze, which means run the code and catch bugs. Crash course on MPI, which is a very small segment of MPI. It won't be that long anyway. If you don't know MPI, you'll like our brevity. If you know MPI, then also you'll like your brevity. Okay, both these will be happy. Okay, so we are not going to give you all the 300 plus commands and variations. There are 12 types of sends and receives. Okay, that can. I don't know who uses all of them, but some people will need some of those send types sometimes. That's why they are all there. And experts know it all. Users will know typically 4 or 5 variations of it. So we'll introduce 4 MPI functions and call them by simple names for some discussions. Some discussions we'll use the full names. The names are send, receive, wait, and barrier. They are very specific commands I'm talking about. The actual send I'm talking about by the letter S is MPI_send. That's the function name. Sometimes I'll call it iSend. I leave out this MPI_. It keeps happening all the time. iSend is an immediate send. It's of interest because it's one of the simplest forms of send. You start a send. That's what it does. It doesn't really mean that the message has been finished in terms of transmission. iSend. I don't know why they called it immediate, but that's the historical name. iSend. iSend goes as a matched pair with wait. So the usual usage pattern is iSend, where you start a send, and somewhere down in the code path you will find a wait. At that point, by the time the wait is hit, the send should have drained the buffer from the memory of the sending process to some area outside the process. That's all it means. When that happens, the wait can clear. Where can the message be after you have drained the message? Well, if the system has system buffering, then it could be parked in the system buffer out there in the cloud somewhere. The receiver may not have seen it. But if the system buffer is short in supply or it has been allocated to be extremely small, then the send process cannot finish, i.e. the wait cannot unblock itself until and unless the receiver also has meanwhile come and absorb the message. So that's how it works. So start a send and then do other computations. You don't just idle, start a send. The reason that these split operations are often used is that when you start a send, you have other work to do. So you send other compute or send or receive. Wait comes later. So this is a good pattern to use. We'll see that in some codes. Many codes don't even use this detailed variations. They simply use isend and wait occurring together. So they just start a send and they want to finish the send before doing anything. So this is the full name, as I said, is MPI underscore send. That's how in the standard publishes it, MPI underscore send. Sorry, MPI underscore isend. I'll write it once at least. And this is written in the standard as MPI underscore wait. If you use isend and wait together, it is as if you wrote the MPI command MPI underscore send. So the I goes away. And so MPI send means a pure high level send where you started the send and finished it, because it is like isend and wait together. So the split operation business is not there. The window of okay, you get the idea. All right. So there are some non-overtaking rules of MPI which are very well thought out, which means if you have processes, process 0, process 1 and process 2, suppose I do some send type, I will not say what type it is, to P1 and then the message payload here, then later send to P1 itself some message M2, then the receives posted by process P1 must pick up the messages in the same order. That is called the FIFO ordering. So it is as if you are sending it through a FIFO queue so that the send order is preserved when you receive. So point to point non-overtaking is the idea. So later sends cannot be received earlier if it is between one pair of processes. But between different processes there is no such restriction. So if I say send to P1 and P1 is here, P0 is here, P2 is here, then I say send to P2 of some message. This has also a message. There are many arguments. I'm just showing the message, and then it is sending to different processes. This can finish before the other one. So if you send to different targets, this can finish before. The idea being that if this is a huge message and if this is a short message, you don't want the short message to wait for the huge message. So in that case, for different destinations, it doesn't matter. It can finish in different orders. Things like that are designed, well thought out and designed. So send and receive are basic primitives, and isend and receive fused together is interesting primitive. And then you have wait. Wait finishes off isend or I receive. So I said 4 letters initially. Send, receive, isend. I'm using S for isend for now, R for I receive. What is I receive? Okay, I receive is the matching companion for receive. So if some process P2 says IRECV, MPI underscore IRECV of some arguments, then again it only starts the receive, meaning it has a buffer into which the message is flowing into. You shall not even look at the buffer till the matching MPI underscore wait happens. What is a matching wait? There is a way to couple. Yes. Sorry. Yeah, thanks. I sometimes forget that. Okay. So thank you. So thank you. I will start again. So there is a notion of a split operation for the receive side, which is MPI underscore receive and MPI wait. Again, the idea is that the receive activity may last a long time. You don't want to preclude other things from happening. So you can say other useful stuff can happen here, and then you wait for the receive to be completed before you touch the buffer. So you can say OK to touch buff here. So the buff is tied up. It's a big chunk of memory usually. These messages are large. So you shall not look at the buffer. You can't even read from the buffer. It may page fault or crash. The operating system may lock it in a special status. So that's how bad it is. So start a receive, go do other things, and when you are ready to process the buffer, you can do it. But if you don't want that much generality, you can write MPI underscore I receive immediately followed by MPI underscore wait. And there is a way to couple these. I'll come to the detail later. But basically, you will mention some common handle between them. MPI underscore receive gives you a certain handle saying that's the receive I'm talking about. The wait will mention the same handle. So they are going together. Okay. There could be multiple such windows opening up. I receive 1 with its wait 1 in process. I receive 2 with its wait, but they all know which wait goes with I receive. We'll show the syntax details later. But if you write it this way, then it is equal to the MPI command, MPI underscore recv. So in many programs, it's perfectly okay to use just this variation because it's trouble-free, it kind of works. And you may not need this luxury of do other stuff here because you may not have other stuff to do, or you have written the code in such a way that all the busy work you could have done is moved outside, etc. The other construct I talked about briefly is barrier. Barrier is like the barriers we briefly talked about. MPI also provides a barrier construct, and barrier, I'm going to use the letter B. Sometimes I'll start using the full name. Barrier is a command that all processes should mention, and then so this at some code point talks about a barrier, this talks about a barrier, which means all their computations should arrive at the barrier before anybody can go past it, which is again, sorry, I was not careful to show this. I will remember it now. So all these processes must reach their corresponding barrier before anyone can go past it. That's basically it, and its full name is MPI underscore barrier. Barrier is one of the simpler forms of collective operations. Collective operations are a large group of operations within MPI. There are 20, 30, 40 different collectives. Barrier is the simplest collective. All it means is that all the processes must execute that operation at the same time, collectively. So the call doesn't make sense only if some of the processes execute the barrier, the others don't. Most likely you will get a bad deadlock and the system will hang. Okay. Sometimes the collective operations have some asymmetry. There is a bcast operation, broadcast. I will not talk about more of it now, but I'll mention its existence. So I'll call it bcast for now. So bcast is a broadcast operation, and again a collective. The idea is that all the processes must participate in a broadcast. But in reality, one of the processes will be the process broadcasting, and the other processes are going to be the ones enjoying the broadcast or receiving. So if process 0 is broadcasting, if the ID of the process matches this argument, then that is the process broadcasting. But if these IDs are different, they are the receivers. So the call will look the same. But since you know where this broadcast is occurring, you can then decide who is the originator, who is the consumer. So that's another example of a collective operation. You can ask whether one process can broadcast and go away. No. I think there is a slight asymmetry there. It's like a barrier, but it's almost a barrier. These guys are all receivers, so none of the receivers can proceed past the broadcast activity till all of them have arrived, because obviously the sender has to initiate the broadcast, etc. So it's almost like a barrier in that respect. A full barrier means everybody has to arrive before anybody can cross. Here, if you read the standard carefully, you will understand that the sender is allowed to proceed as soon as it has initiated the broadcast. Some of these I dredge from my memory, like humans have fallible memory. Human memory is never perfect. I don't program these days. But some of these facts I am pretty sure is the case. But it's always a good idea to read this MPI standard once again, just one paragraph of it, just to make sure, okay? It's always safe. I'm not trying to hide anything or quickly say and move on, but there is an asymmetry for many commands, and I happen to remember it well. But check again. Some of these commands have undefined status in MPI. If you don't do it in a certain way, what happens is not fully defined by the standard. So those cases are very, very important. If the standard doesn't say something, don't assume the wrong thing. It doesn't. It may crash, things like that. So some MPI implementations may have restricted the barrier to have a broadcast to have a barrier semantics. But generally, it's not a good idea to rely on these slightly liberal behaviors. Treat it as a barrier. That's always safer. Yeah. All right. So this is the basic understanding of broadcast. Send and receive. So I have details here. MPI send, destination, message buffer, request structure. Now comes the detail of MPI send. So this is a non-blocking call, like I said before. Start copying out the message buffer. Starts a memory-to-memory copying from the issuing process to the destination process. But like I said, this may benefit from runtime buffering. If the runtime buffering is there, the send can drain quickly and move on. Otherwise, it sort of has to wait for the receiver. Because there is no runtime buffer, it has to hand it directly to the receiver. Handover. Then the MPI wait of that request structure. So the same request structure must be mentioned in the wait, and then they are going as a matched pair. That then signals the completion. When this wait will block, that process is completely blocked in that wait. It can't proceed even 1 millimeter past it till the message has gone out. When the message has gone out, you will see the program counter of that process moving forward. So then as soon as the wait clears, you can reuse the send buffer. Again, till that point, the send buffer is tied up. You cannot reuse it. If you try to write into it or read from it, bad things can happen. These are expensive resources, by the way. MPI is a system which is really subject to denial of service if you do it the bad way. I mean, imagine 20,000 processors sending a humongous payload of a megabyte to one process. And who says that the system should have buffering? You know the denial of service attacks in internet, right? I mean, you can choke a cloud service completely down. MPI tries its best to avoid these problems. So MPI provisions buffers sufficiently that receives are possible. Some MPI runtimes are smart enough to have a credit-based system. So the more you send, the less send credit you have. And the send credits are returned to the sender when the receives happen. There are mechanisms underneath. So it kind of implements a flow control like that. So with all that, there is no retry also. In sockets, if you send, there could be a status bit that comes back saying the send didn't succeed, and in sockets, it's possible to retry. But in MPI, it's a very brittle thing. The send happens or doesn't. If the MPI send is hit with a electrical fault or alpha particle or something corrupts in the memory and the send fails, MPI is very brittle. The whole MPI system crumbles its state. people are working on fault-tolerant MPI, where the fault-tolerance mechanism kicks in and restores. But as such, MPI is not entirely capable of handling faults. So there are some disadvantages in the modern sense for MPI send and receive. They are not robust operations like one likes to be. Okay, so MPI receive is source, message buffer, struct. This is a non-blocking call. Starts a memory-to-memory copy. MPI wait finishes. Okay, so now we're going to illustrate two programs for you, just to show how the interplay between sends and receives and waits proceeds. One is lucky, one is unlucky. I think this is lucky or unlucky. We'll see. So based on where I put the sleep, it gets lucky or unlucky. We'll see. Okay. So example of program lucky. Lucky. Okay, I remember the joke now. Lucky for the programmer that they found the bug. Okay, that's how it was designed. Because if there is a failure waiting, you should know it. That means you are lucky. That's always good. So let us say that this sleep is commented out. This sleep is 3 hours or so, whatever it is. OS delay, whatever. So this is send to 0. This is not how it's written. It's good for pseudocode. Send to 0 with the request handle. Send to 0 with the request handle. So both are contending to send to 0. What is 0 doing? There is an option called receive from star. You don't need to mention a specific receiver. You can also say wildcard receive. Say I'm open to receive from anyone. There is no wildcard send. Okay, that's bad. I can send to any one of you. Doesn't make sense in a program. But I can receive from anybody is sensible. We'll show an example of its use very soon. So in this case, whoever comes first is the one that gets picked up. So this gets picked up. Now this is bent on receiving from 2. So I have one more frame. That's the state of the system, where this is now trying to send to 0, but this receive is essentially trying to receive from 2 at that point. So they don't match. The details are not fully worked out. I am only giving the high-level idea, but because the reason I say that is this R and S are not blocking sends, they are non-blocking sends. Like I told you, this S means I send, which means start a send and proceed. So this send will in fact proceed till its wait. So that's why I say all the waits can be piled up here. So if this is an immediate send IS, its wait can be put here. If this is an immediate send I send, this is an I receive, this is an I send, you can pile up all their waits here. I don't care. That's what I meant by this code. But we can work out the details. But the upshot is that this system will reach a state where this send to receive match will never happen, meaning the corresponding waits will never clear. The whole system will be gummed up. That's the effect you will get. Okay, you can. I'm suppressing some details here. Whereas if I now change, this is now the unlucky, because the unlucky for the user that they didn't see the bug. So this is in testing. You don't see the bug. Suppose I put the sleep here. Then the speed of this is delayed, so this matches. And then this send to 0, receive from 2 matches. Send to 2, receive from 0 matches. Send to 0, receive from star matches. No deadlocks, all the waits will clear. So all this shows is that in certain codes, especially codes where there are these wildcard receives or star receives, it is possible for the speeds of the process to land the process into trouble and deadlock. In programs where there is no use of wildcard receive, all are specific receives, then if the code is going to deadlock, it will always deadlock regardless of the speeds, like that. So this is a non-deterministic operation, and based on the non-determinism, how the non-determinism resolves may or may not deadlock. More MPI commands, MPI barrier. I told you about the fear of the unforeseen. Some barriers are put in just to align the processes. Sometimes the barriers are put because people think unless they align the processes at that point, there will be bad interactions between executions before the barrier and after the barrier. They haven't thought through it enough, so they put a barrier anyway. So there is a paper where they argued a barrier, removed it, and found it was necessary. So we wrote an algorithm long ago. It's in a paper form. It's implemented in some places to find all functionally irrelevant barriers, or fibs. So we wrote a little analysis program to look for useless barriers to remove them. It is possible in many cases. Saying that you don't need a barrier, all the other synchronizations are giving you the effect of a barrier. This is just slow down. Okay. This is not a puzzle I'm going to solve. This was done many years ago. So I challenged the audience, so do you really understand these commands by now? Then I wrote a one-line program and asked the audience to solve it. And these are the things that the MPI standard allows, but nobody writes such code. But as a programmer, should you be able to answer these codes? Think about it. So in C, if I write a code, as of I++ gets I++, or as of I++ gets as of I+++++, should you be able to think about it and decide what's going on, right? As of index I++ equal to as of index I++, the whole thing plus plus. Well, as a programming language, you should be able to think through it, and there is only a definite answer. You can't have compilers produce two different answers. It used to happen. C programs were notorious for that. In the 80s, I used to have fun writing these kinds of codes and running it in different machines, and they all vary. But these days, that much has been standardized, and you don't get surprises with codes like this. You may think nobody will write it, but these days, people are not the ones writing the code. Other codes are writing codes, right? Auto-generated code. Auto-generated code is plug ugly. So in auto-generated code, anything is possible. So unless these cases don't give you unique answers, you are in trouble. So it is important to answer every corner case. So this is a corner case where, thank you. I saw that the MPI standard doesn't preclude sending to yourselves and receiving from yourselves. Okay, so you can make an example. So process 0 saying, receive from myself to start with. It's possible. Then you say, I'm having a barrier. Then I say, okay, and now I'm sending to myself. And then they wait for this guy, and then they wait for this guy. And there is a way to solve it. You have to really know the exact execution mechanism of the MPI, which I won't detail now. But the basic idea is that this receive from myself is immediate receive, or I receive, like I said. Okay, I receive only start the receive, so they can proceed. The receive hasn't happened, it can proceed. Then it will hit a barrier, and this is a single process program, so obviously the barrier will clear. Then the send to myself with some message I don't show can be started. So happily the process is sending and from itself to itself. Hopefully they are using different buffers, otherwise there is already trouble. So this buffer can be different from this buffer. That's fine. So at some point these send and receives will complete, and when they complete, the receive has fulfilled its desire. This wait will clear, then this wait will clear, things like that. So this will not deadlock. But if you now shift this wait operation to before the barrier, this code will deadlock. So I'm just saying that if you look deep inside any HPC standard as a very caring, discriminative programmer, you will find cases where the standard doesn't answer. So then you have to recruit 3-4 PhD students and research it and do a better job. That's the only answer now. Short-term answer, ask the world's best experts. And sometimes they are also not sure. So then the standardization committee has to take it up. So we are not in a game of blame. This is unfortunately, this is not a place where a company produces a product and the customer takes the product. Customer finds the product defective and sues the company. That's not the arrangement here. MPI is designed by people like us who just want to do the world good. OpenMP is designed by people who do us the one. So MPI is promulgated by the MPI forum. So you become a member of the MPI forum on your own because you want HPC to happen. Companies, of course, fund these forums and hire our students, and they take up MPI produced by the open source movement, and they produce Intel MPI, things like that. So there is that exchange. So generally, these things are resolved when standardization committees meetings happen. You can join a teleconference and opinion, and the next time they revise the standard, then they may tighten the standard, make sure that the manufacturers adopt it, it gets released. So usually in centers, MPIs are much older than the latest MPI. I'm just saying the process of blaming is not generally, I mean, instead of blame, one should try to improve the system. That's how this community works. So I respect that. So it's generally when we find bugs in this case, we just try to work with somebody who cares about the MPI forum. Okay, so all right, so let us now read some code and start understanding. Okay, just one more little thing, then we'll do it. So we wrote a paper where we showed cases like this, and I don't need to get into details, but in a paper we try to highlight unstated but important to know behaviors of MPI. So we showed an example where by adding more buffering to the system, meaning allowing the system to absorb your message and keep it pulled away from you. So more buffering means more progress, okay? So generally sends and receives like to progress as much as they want to. And if you provide system level buffering, a send can issue, copy it into the system buffer and move ahead. So the general assumption is that the more buffering you add in the system, the more progress, less deadlocks. But you can easily create examples where if you increase the system's generosity with respect to buffering, you can cause the system to deadlock more. This is like the popular adage, if you give too much rope, they will hang themselves. Okay, that happens here. So this idea is that if you give too much buffering, certain commands start running ahead, and then they start matching these wildcard receives prematurely, and that blocks somebody else to match. That's what happens. So and whenever there is non-determinism, a lot of intuitions are going to go bad. We even created a third example where you have to allocate a specific buffering to cause a deadlock. This end has a lot of buffering. This end doesn't have that much buffering. This receive has a lot of buffering. This doesn't have. So we can even create a situation where based on the amount of buffering available to sends and receives, you can land the system into trouble if you don't have. So it's a hard problem, and deadlocks are bad because deadlock, the net effect of deadlock is you run a compute job, and after some time you see nobody progressing. All the calls, MPI calls have been issued, no call is returning, and those are hard to diagnose. It happens. And then you eat up your supercomputer time. Okay, this is all just to give a perspective that I have. Let us now read some codes. So this is thanks to my supercomputer center. Their references here. They produced extremely simple examples that were just a page of code. So let us read the Pi serial and understand it, and then we'll go to Pi OpenMP, since it's a good refresher. Then we'll do Pi MPI, then we'll do Pi MPI plus OpenMP. They're all short, and we can run it also. So main int argc argv, some large, same Pi example. It was started by Tim Madsen, everybody uses. See, GIAn also used the same example. Yeah, so constant double. Let us, read the code from here. Start a timer, sum equal to 0. We are doing a long series addition. Basically, the series addition is for every number in the range, you are going to calculate a certain x value, h times, I don't know the logic well, I mean, I used to probably at one point. It's not Monte Carlo. He said it's Monte Carlo. It is not Monte Carlo at all. I mean, he quickly mentioned Monte Carlo. Yeah, this is a series. I think it's a tan inverse something, okay? It's related to tan inverse expansion, that much I remember. It's a series solution, okay. I'll tell you which identity it is. So anyway, it's some kind of an identity like that. So it is basically doing a long addition, and then finally when the range is exhausted, pi keeps accumulating h star sum. I forget the exact detail, and then it's adding to the timer. Then it is seeing how much error there is between pi, and capital Pi is up to a lot of digits, and then it prints. Okay, so let's, I can run it, but let's look at the OpenMP code. So what's the difference with OpenMP? The range is split. That's the news. There is nothing surprising. The entire range is not done by one thread. You do it over multiple threads. So pragma OMP parallel for, this is well written, shared N and H. He makes sure that the N and H are shared by all the threads. But N is read, H is read, both are shared and flowing from the previous context. Private IX, which is a nice declaration. So you don't need it. You don't need to say private I. It's automatically private. The iteration variable on which you apply an OpenMP for is private, but good programming practice to say it. And if you make an error, you will catch it easier. X is also shared, so this is a thread specific X, and reduction is a plus, reduction of plus for the target variable sum. So pretty much the thread team comes here and does the series calculation. All the threads are doing their work, and finally you get the same answer. Okay, that's OpenMP. Okay, any questions? This is pretty much the first OpenMP parallel for that we saw. The idea is the loop is parallel because there is no inter-iteration dependency. You can run this loop in any order. All it is taking is the current index and calculating this quantity. So the loop iterations are parallelized, parallel, and they can be run. It's okay? Yeah? Yeah. This is OpenMP. As soon as the pragma OpenMP happens, it's that's at least contains OpenMP. Then you have to further look to see if it has MPA calls. Then it is MPA plus OpenMP. We'll have an example that contains both, and you can do that. Okay. So this only has OpenMP commands. So far as we know, it is OpenMP. Yeah. Yeah. Discussion. Okay. Yeah. I was also this programmer is very interesting. Says time minus equal to a timer, time plus equal to timer. That's interesting. Probably it will get that. I wouldn't write that. Why is it writing all that? I have no idea. Yeah. Whatever it is. Huh? Okay. I know, but we could have used. Yeah, okay. So it is snapshotting. Okay, I think that's good. So C timer grabs the current time, and then he is avoiding a later subtraction. Okay, that's his style to do it. Okay, I would have written T1, T2, and then T2 minus T1. That's clearer. Okay, this person is interesting. Okay, all right. So PyMPI.c. Okay. What is the MPI program doing? Okay, let's read it carefully. This is probably the first MPI program for some of you, maybe. Okay, so it keeps coming as if it is. So what is MPI? It's MPI single program executed across a collection of nodes. If you run do MPI run, it starts the MPI on the rank 0 node, and then the other processes also have the code. They all are woken up. There is a certain mechanism in the MPI involving daemons and things like that, which I sort of know. Automagically, it all wakes up. There are processes created. You don't need multiple nodes. You can run MPI on your own multi-core, and you can see that each core picks up a process. That also happens. Okay, this is another quick way to get parallelism if you don't have anything else. You can run MPI, and each core is running a process, not a thread. That's fine. Processes are heavier weight entities with its own complete closure of memory space and all the file descriptors and everything. But a thread is not. So yeah, you can run it anywhere. It has a notion of process. MPI init is the way to start an MPI execution. It must be there as the first command. It typically gets passed in the same argc rv. So the details are, I don't remember it. It is a convention. There is a certain detail you need to read about MPI init. I don't do it. Usually when I do MPI init, I pass null, null. That's allowed. I don't care. I don't want to specialize init in any way that I care. ComRank is going to return my rank. So MPI commands are all old style reference passing things. So you pass the address of my rank variable, and when the call finishes, you have the value returned. So arguments pass the values in and out in many cases. So ComRank. Then ComSize says how many processes are there. So this is bound to nproc based on the runtime command. So when I run this program, I do MPI run. Let me see, my internet is there. Once again, I don't have MPI installed on this Mac laptop. Oh, it came back. So all the characters are going halfway around the world, which is not too fast, it's not too slow. Oops. Okay. This is how you compile it. That's how it works. So NP4 is going to set com size as 4, and the processes know their ranks. It calculates pi with a tolerance, and it tells you the time. So that's so the com size. Now you know where com size got the value from the runtime parameter. My rank is each process knows what rank it has, its ID by the system. Then you can do MPI W time. MPI has timers. So now what I am going to do, who is I here? Who is running this code? Well, all the processes are running the same code. Much like threads are running as a piece of code, all the processes are running the code you are seeing. Till you split based on your rank. So sometimes you say I am rank 0, then I do that, others. So SPMD, single program multiple data kind of thing. So for each process says I'm going to start the iteration from my rank. So process 0 will start its iteration from 0. Process 1 will start its iteration from 1. So this is a distribution. We saw this. If this is an array, we know what kind of a distribution we are looking at. It is stepping by nproc. So I think it's a click. Yeah. So 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4. I'll pick up that number and do the addition. So they are all working, and automatically there is no private or anything now. Why? Because all the variables you see here are private to the process. So these variables are private to the process. There is no shared anything. Okay, so this is a program where there is perfect isolation. All the variables are variables that are declared for this process. So happily, each process is taking its own x variable and then adding into the x the effect of this partial sum. So let us say process 0 goes from 0, then if there are 4 processes, the next thing it will add is 4, then 8, then 12, 16, etc. So it has a certain sum, partial sum only for those points in the series. The other process 1 has other points in the series already, but they need to be brought together. So when it's needs to be brought together, you make all the processes execute MPI reduce. So in this, like the reduction of OpenMP, you are going to make them all do an equivalent operation. So this is a collective operation. So this line of code is being run by all the processes.